Hi, this is Mrs. Villette, and this video is on the mean value theorem. I'm going to go through this first part pretty quickly because it's mostly reading, so you can always read over it if I go too fast. Let's start with an introductory example of what the mean value theorem is trying to say. So this is actually a real thing. It hasn't happened, but some states have proposed instituting automatic speeding tickets based on how long it takes you to travel between certain checkpoints on toll roads. So if they know what the speed limit is, in this example, we said 60 miles per hour, and a section is 10 miles long, we know that if you're going the speed limit, it should take you exactly 10 minutes. So let's say you drove 10 miles and it took you 9 minutes. Does that mean you were speeding? Well, one thing that we could look at is we could just look at the average speed. In this case, the average speed is the same as the average velocity. So we could say that we went 10 miles and it took us 9 minutes. Now that gives me a rate that's in miles per minute. So let's go ahead and multiply that by 60 minutes per 1 hour. And now we have a rate that is in miles per hour. So we have 600 over 9 miles per hour, which works out to be about 66.7 miles per hour. So I would say that yes, we were speeding. Our average velocity or average speed, in this case since it was positive, was 66 2/3 is what it actually worked out to be miles per hour. And one of the principles of averages is that the average has to be lower or equal to the maximum value. So that means that the maximum speed was at least 66.7 miles per hour. And in all probability, it probably varied, went below and above, but we were definitely above 60 miles per hour at some point. So our instantaneous speed was higher than the speed limit. So we're just going to translate this into symbols. So we're going to use S of t for our distance in miles, traveled in t hours, and our t is going from 0 to 9/60ths. The reason I chose 9/60ths was to go ahead and get rid of that conversion factor that we needed to do right up here. So S of 0, our position at time 0 is 0, S at 9/60ths, so our distance after 9 minutes is 10. So if we look at the slope of the secant line, then we're doing our S at 9/60ths, which is 10. So we're doing 10 miles minus 0 miles over 9/60ths hours, not minutes, minus 0 hours. And that ends up being 10 miles over 9/60ths hours. We invert and multiply, and we are multiplying by 60 over 9 hours, and we get the same answer that we got up there. So we're essentially just calculating a secant line. And I realized later down here I forgot to change this function to s. So the slope at any point is given by the derivative. Since the average value is greater than the speed limit, this is basically what I just said, there must be at least one point where the instantaneous velocity is higher than the speed limit. So there exists a c value where s prime at c, so my velocity, is equal to the average rate of change, changing these to s's, on the interval, which is 20/3, which is actually what this fraction over here reduced to, for some time between 0 and 9/60ths. So we're going to talk about this more generally, not with a position function, but just any function. So we've got a y equals f of x and a range from a to b. Does the value of the derivative at some point between a and b have to match the slope of the secant line connecting the points, connecting our endpoints? So we're saying, does f prime of c equal f of b minus f of a over b minus a have to hold for some c between a and b? So this seems pretty reasonable. I'm going to draw a function. So here's our kind of arbitrary calculus-y function. And here's an endpoint a and b. Let's go ahead and find the points that correspond to those, and then draw a secant line. So for this particular function, here's my secant slope, and I think I can pick out a place, it looks like about right here, where the slope of the tangent line is the same as the slope of the secant line. So we've got our average rate of change over the interval a to b is this slope. And then we've got our instantaneous rate of change, f prime at c. So the c value would be this value right here. So for this particular function, it appears to work. I've got the slope of the secant line, and I've got the tangent line at this point c ending up looking parallel to this secant line. So when does it not work, I guess, is the question. Let's take a look at some examples. We have two functions here, and f sub 1 is 1 over x squared, and f sub 2 is the square root of the absolute value of x. I don't know what that extra little parentheses is doing there. So I've got these graphs shown right down here. So figure 7 is the 1 over x squared, figure 8 is the square root of the absolute value. And we're going to use a equals -1 and b equals 1. So we're looking on this interval here to here on both of them, from -1 to 1. So both of these functions have values of 1 here. So if I draw my secant line, my secant slope is 0 for both of these functions. This turns out to be the case. So both of these functions have a secant slope of 0. But if we look at both graphs, there is never a place on this interval, so we're talking about on the interior of this interval, there's never a place where the instantaneous rate of change or the slope of the tangent line is 0. So I can see on this one, clearly, there's a discontinuity. On this one, it looks like the place we get closest to that is at this peak right here, or this point, but we've already determined that our derivative is undefined at these sharp corners. So let's get to the statement of the actual theorem. When does this idea of the average rate of change equaling the instantaneous rate of change work? Well, it works under these conditions. We're going to let our function be a continuous function on the closed interval ab and differentiable on the open interval a to b. So that just means that it has to be differentiable on the interior of the interval, but not necessarily at the endpoints. If these two conditions are met, then there exists a value c between a and b such that the instantaneous rate of change at c equals the average rate of change over the interval a to b. So our average rate of change, this is the same difference quotient we've seen multiple times. Now I already have drawn a picture on the previous page showing a case where it did work. So let's take a look back at these two examples. The reason these two functions did not meet the conditions of the intermediate value theorem was that this first one was discontinuous, and I said intermediate, I meant mean. So this one did not satisfy the conditions of the mean value theorem because of the discontinuity at 0. And then this one, although it was continuous, did not satisfy the conditions because of the non-differentiability or that sharp corner at 0. So let's look at one more theorem before we do some examples, some actually working out and doing some calculations. The last theorem in this section is called Rolle's theorem. And Rolle's theorem just says that you have a continuous on the closed interval and differentiable on the open interval function where the two endpoint y values are equal. So f of a equals f of b. In that case, Rolle's theorem says there's some c on the interior of that interval such that f prime at c equals 0. So you can see if the endpoints are equal, that the average rate of change is 0. So Rolle's theorem is really just a special case of the mean value theorem. So if the two endpoints are equal, the average rate of change is 0. So Rolle's theorem just says there's some place where the instantaneous rate of change would be 0. So example 2, we are going to draw a function where Rolle's theorem would apply on the interval -2 to 3. So I'm going to just pick a point at -2. If I want Rolle's theorem to apply, the function has to have that same output at 3. And then I can do whatever I want so long as I am continuous and differentiable. So that means I need to connect these smoothly with no vertical tangents, and that was not so smooth. Let's go simpler. Let's just do something like this, something parabolic looking. So I can see right here is the c value where the f prime of c is 0. Notice that Rolle's theorem and mean value theorem don't tell you how to find that value, they just tell you that it exists. Let's go a little bit broader here on this last example using the actual mean value theorem. So we're going to consider the square root of 9 minus x squared on the interval 0 to 3, and we're actually going to find the c in 0 to 3 that satisfies the mean value theorem. Let's start by evaluating our function at the endpoints. So we're going to find f of 0, which is the square root of 9 or 3, and we'll find f of 3, which is the square root of 0 or 0. So we've got these points here. Now hopefully you recognize that this is the top half of a circle. So this is just a semicircle of radius 3. So I'm going to do my best to draw something that looks fairly circular. And really we just have a quarter circle because we have the top half and then we've restricted ourselves to the interval 0 to 3. So we've got just a quarter of a circle. So the mean value theorem says there is an f prime at c, so there's some c, where that instantaneous rate of change is equal to the average rate of change. So let's calculate this right-hand side first. So our average rate of change, we are going to do 0 subtract 3. So I am doing the outputs, 0 subtract 3, over 3 subtract 0. That is my inputs, and this ends up being a slope of -1. We probably could have fairly easily seen that graphically if we had just drawn that secant line. So our slope here is -1. Now visually I can see where it appears that I have a slope of -1, which is about right there. So here my f prime of c also equals -1, but we need to figure out where that c value actually is. So we need to find the derivative. We've already calculated that I want my f prime of c to equal -1, so now I actually need to see what my f prime is. So my f prime of x is the derivative with respect to x of the square root of 9 subtract x squared. We need to use the chain rule on this one, so we're taking the derivative of the outside at the inside multiplied by the derivative of the inside. And the derivative of the inside is -2x. So I have -2x over 2 square root of 9 minus x squared. I can cancel the 2's. And now I want to set these two things equal to each other. So I want f prime at c, which needs to be -1, to equal this x over the square root of 9 minus x squared. So I'm going to say, oh, and actually it was negative. So negative x over the square root of 9 minus x squared equals -1. I'm going to multiply across or clear fractions. So negative x is negative square root of 9 minus x squared. Now I'm going to go ahead and square both sides to get rid of the radical. So I get x squared equals 9 subtract x squared, or 2x squared equals 9, or x squared is 9 halves. So x is the plus or minus square root of 9 halves, which when I rationalize and simplify gives me 3 square root of 2 over 2. Based on the interval I am in, I'm going to choose the positive square root. If you notice, this is the same thing as 3 times the square root of 2 over 2. If you recognize that the x is square root of 2 over 2 on the unit circle at 45 degrees, this stretch factor is just my radius, so this x-coordinate is just at a 45-degree angle on a circle of radius 3. So looking back here on our graph, if I draw that 45-degree angle, that's that point right here, so the x-coordinate is 3 root 2 over 2, and since we know that this is on the 45, the y-coordinate is the same. Our overall conclusion, though, is that our c value is 3 square root of 2 over 2. So we'll write our conclusion right down here. C equals 3 square root of 2 over 2. And that's it.